You ever feel like you're just drowning in new information? Like one minute you're trying to wrap your head around some scientific paper, the next there's this huge shift in AI, and you just wish there was a shortcut, right? To really get the core idea, not just skimming the surface. Well, today we're actually going to dive deep into something that might just be part of that solution. It's a really fascinating new paper from Meta's FAIR team. The title is From Bytes to Ideas, Language Modeling with Autoregressive UNets. We'll just call it AUNet.
Rolls off the tongue a bit easier.
Definitely. And our mission here is to unpack how this AUNet idea tackles a really fundamental challenge in AI. Basically, how language models actually read, understand text.
Yeah, it gets right down to the basics.
Exactly. We'll look at why this matters for where AI is going and some of the pretty surprising things it can do. The big question really is, what if a language model could learn to process text directly, like raw data, without needing a fixed dictionary up front?
Interesting premise.
Let's get into it. So before a language model can even start predicting what word comes next, it needs to figure out what the pieces of the sentence are.
Right, the basic units it works with.
Think of it like prepping ingredients before cooking. You got to chop things up first. In AI, this chopping process, it's called tokenization.
Tokenization, yeah.
And the most common way models do this is using something called byte pair encoding, or BPE.
BPE,
The basic idea is it looks at a huge chunk of text, finds pairs of characters or bytes that show up together really often, and merges them into a single token.
So like T and H become the.
Exactly. Then maybe the and E become B. It keeps doing this until it hits a vocabulary size limit you set beforehand.
Okay.
So you've got these two main levers, right? The text you train on the corpus and how big you let that final vocabulary get.
And what's really key here, the fascinating part, is that this traditional tokenization, like BPE, it forces a fixed granularity onto the text.
Fixed granularity.
Meaning it decides up front what counts as a word or a piece of a word, and that's it. It's like freezing the model's view of language right at the beginning.
Ah, okay. So it makes that decision once, and the whole model is stuck with it.
Precisely. And that causes a few, let's say, interesting issues. First, that vocabulary is static, locked in.
Right.
Second, each token gets its own unique code, its own vector. They're sort of opaque identifiers.
Opaque?
Yeah, like the model doesn't automatically know that apple and apples are related, even though they share almost all their letters.
It has to figure that out from context later.
It has to completely relearn that relationship from scratch.
Yeah.
They're just two different items in its dictionary. This really holds back what we call symbol-level reasoning.
Okay, so understanding spelling, maybe grammar subtleties, that gets harder.
Much harder.
Yeah.
And think about transferring to other languages or dialects. If their words aren't in that fixed dictionary, well, tough luck. And finally, it's usually done before the main model even sees the text. A pre-processing step. So that single level of granularity, that single way of chopping up words, is locked in for every layer of the model.
Okay, so if the old way is like building with fixed Lego bricks, maybe not always the right shape. What's the AUNet idea? How does it change things?
Right. What if the model could kind of mold its own bricks as it goes?
Yeah.
That's basically the core idea behind AUNet. It tackles these limits by learning to understand information directly from the raw bytes, ones and zeros, essentially.
No dictionary lookup first.
Nope. Instead, it uses attention mechanisms. Think of attention as the model learning, dynamically, what parts of the input are important right now. It uses this to embed tokens on the fly.
So it figures out its own pieces as it reads.
Exactly. And it can do this at multiple levels, multiple stages of splitting the data, all inside the model itself.
Okay, tell me more about these levels.
So it creates this multi-scale view of the text. It starts with the raw bytes. Then it learns to pool those into something like words, then maybe pairs of words. And it can go up to chunks of maybe 4 words.
Wow, okay.
You can picture it like a U shape. There's a contracting path where it compresses the information bytes to words to bigger chunks.
Compressing down.
And then an expanding path where it reconstructs it. And crucially, they use skip connections.
Skip connections, like shortcuts.
Sort of, yeah.
Yeah.
They pass information directly from the early compression stages to the later expansion stages. It helps preserve the fine-grained details, like spelling, that might get lost in the compression.
Clever. So different levels handle different things.
Right. The deeper stages, working with the compressed view, are better at predicting further ahead, looking at broader meaning, semantic patterns.
The big picture.
While the earlier stages, closer to the bytes, handle the really fine details, It's a bit like predicting multiple tokens at once, but it's baked into the architecture. No extra hoops to jump through.
Okay, this is the really critical part for you, the listener, to grasp, I think. Tokenization isn't this separate step anymore. It lives inside the model.
That's the paradigm shift. It changes everything.
How does that affect things like, well, how it pools information or scales it back up?
Yeah, that flexibility carries through. It doesn't use fixed window sizes like older methods. It uses a splitting function.
Oh, what now?
A splitting function. Right now, it's actually rule-based, pretty simple, like using regular expressions, regex, to find spaces, letters, numbers, punctuation.
Oh, okay, like defining word boundaries on the fly.
Kind of, yeah. And it's designed to be stable, so when the model generates text, adding words doesn't mess up the earlier splits. For upsampling, scaling the data back up efficiently, they found something called multilinear upsampling works really well. Simple, but effective.
And is it efficient? All this byte level stuff sounds computationally heavy.
That's a fair question. The byte level stage is always active, but the deeper stages, the ones doing the heavy semantic lifting, they only activate when needed. It's guided by this cascading conditional activation.
So you only pay the computational cost for deep understanding when you actually need it.
Exactly. It optimizes the resource use.
Okay, so theoretically it sounds great, flexible, dynamic.
Yeah.
But what does it actually do? What are the real-world results? The paper lists some key contributions, right?
It does, and they're pretty significant. First, C1, they call it the adaptive multi-level hierarchy, up to 4 embedding stages, user-defined splitting, much more flexible than older approaches.
Okay.
C2, infinite vocabulary size. Because it works on bytes, there's no predefined dictionary. It can handle any sequence of characters, new words, typos, rare terms. No problem. No massive, memory-hungry embedding tables.
That's huge.
It really is. C3, strong performance and scaling. They show AUNet, even just one level, is competitive with strong BPE models trained for the same amount of time. And the deeper versions show really promising scaling.
Meaning they get better faster as you make them bigger.
Potentially, yeah. C4, practical efficiency. Despite the complexity, the actual speed, the wall clock time on GPUs is comparable to BPE.
So it's not slower in practice.
Not significantly, no.
Oh.
And C5, stable scaling laws. They actually had to figure out new math, new formulas for things like batch size and learning rate to make byte-level training stable and optimized. They documented that too.
Right, because training directly on bytes is different. Okay, that's a compelling list. But the numbers, how does it actually stack up on standard tests, the benchmarks everyone uses?
Yeah, let's look at the results. Overall, when they compare AUNet and BPE using the exact same training budget.
Apples to apples.
Exactly. AUNet consistently matches or slightly outperforms the BPE models. And the multi-stage versions, AUNet 3 and 4, actually pull ahead on several benchmarks.
Interesting. Any areas where it struggled initially?
Good question. On some knowledge-heavy tasks, like Trivia QA, the initial results showed BPE slightly ahead. But they found that this gap pretty much vanished as they scaled up the models and the training data.
So it might just need more training to catch up on those.
That seems to be the case. They did see some diminishing returns beyond 3 stages, suggesting maybe AUNet 4 and beyond need even more data to really show their full potential.
Makes sense.
But here's something really striking. They compared their 1B parameter AUNet and BPE models to a Llama 3.1 8B.
Which is much, much bigger.
Way bigger, and uses something like 100 times more computing power for training. Yet their smaller models got remarkably close, performance-wise.
Wow. So they're getting similar bang for way less buck, computationally speaking.
Exactly. It highlights just how efficient their training setup and this architecture are. AUNet being competitive in that context is seriously impressive.
Okay. And you mentioned math scores being lower.
Ah, yes, on GSM-8K, that seemed to be across the board for all models they tested. So they think it's because the training data they used, this DCLM corpus, just didn't have much math in it.
Gotcha. So beyond matching performance, what about those unique things only byte-level models can really do well? That's where AUNet should shine, right?
Absolutely. And their extended evaluations section really dives into this. Take multilingual stuff. Even though the training data was mostly English, AUNet showed really strong positive transfer to related languages in the MMLU benchmark.
Meaning it did well on languages it wasn't explicitly trained much on?
Yes. Like Germanic languages, German, Swedish, Dutch, saw about a 3-point average gain. Romance languages, Italian, Spanish, French, got a 4-point boost.
Why?
The thinking is that operating at the byte level lets it see the shared patterns, the shared spelling and word structures across these related languages. BPE, with its fixed tokens, often misses that.
Fascinating. What about languages totally different from English?
Good point. For low-resource languages, they looked at translation into English using the Flores 200 benchmark. They saw consistent improvements there, too.
Even if those languages weren't in the training data much.
Exactly. AUNet's flexibility lets it build useful representations anyway. It doesn't need the tokenizer to have seen the language before. That's a huge advantage for less common languages.
Okay, that makes intuitive sense. And character-level tasks, like spelling.
Right. On things like fixing typos, reversing words, inserting or deleting characters tasks in the CQ benchmark, AUNet performs strongly.
Better than BPE.
Often, yes. Though BPE tended to be better on tasks involving whole words. Which makes sense, right? It's a trade-off. Byte-level models are naturally good at character stuff.
While token-based models are more geared towards word-level stuff.
Precisely. So AUNet has a clear edge where that fine-grained character understanding is key.
This is all super impressive. But, okay, let's peek under the hood again. How do they actually implement this efficiently? You mentioned some things earlier.
Yeah, so technically that multilinear upsampling we talked about turns out to be effective and relatively simple to implement. Big win there.
Okay.
For making the training feasible at scale, predicting the best settings hyperparameters is vital. And as we said, they derive specific formulas for batch size and learning rate just for AUNet's layered byte-level nature.
Right, the scaling laws.
Yep. And then there are the engineering tricks. They use sequence packing, basically stuffing multiple short texts together efficiently to keep the GPUs busy.
Smart.
And fully sharded data parallelism, FSDP. That's a technique for distributing these enormous models and their training data across many, many GPUs without everything grinding to a halt.
Spreading the load.
Exactly. Plus, tools like torch.compile to automatically optimize the underlying code for speed.
Got it. But you also mentioned a compromise.
Ah, yes. Even though the pooling is adaptive, to make torch.compile work really well, they actually set a maximum sequence length for each stage. It's a practical trade-off between full flexibility and computational efficiency.
Makes sense. No system's perfect. Are there other known limitations or areas they're looking at next?
Definitely. That rule-based splitting function using regex, it struggles with languages that don't use spaces to separate words.
Like Chinese or Japanese?
Exactly. Their Chinese MMLU scores were lower than BPE's, likely because of this. So future work is about having the model learn the splitting function too, rather than relying on predefined rules.
Ah, letting the model figure out the boundaries itself.
That's the goal. Also, apparently, FSDP, the parallel training method, can sometimes struggle to perfectly overlap the calculations and the communication between GPUs at the higher, more compressed stages of AUNet. It needs a certain amount of input data to run optimally.
Okay, so some engineering challenges still to refine. But overall, what we've really explored today is, well, it feels like a fundamental shift, moving away from these fixed, rigid dictionaries, the tokenizers that we've used for so long.
It is.
AUNet gives language models a much more flexible, adaptive way to see and understand information, starting right from the raw bytes.
Yeah, this deep dive really shows how rethinking something as basic as tokenization can open up big possibilities. You get models that aren't just competitive performance-wise.
Right.
But they're also inherently better suited for handling lots of different languages or tasks needing that really fine-grained character-level understanding. It's about building models that get information at multiple levels simultaneously.
Truly well-informed, as the paper puts it.
Exactly, without needing that pre-chewed input from a fixed tokenizer.
So here's something for you to think about.
Yeah.
Imagine a future where AI can truly understand and speak any language, any dialect, maybe even highly technical jargon, with the kind of nuance a native speaker has. And it does this without ever needing a specific dictionary built for that language or that field. What would that level of, I guess, linguistic fluidity actually mean? How could that change how we communicate globally, how we access knowledge, or even how we interact with AI itself?